next speaker is a professor of mathematics at Purdue University. He holds degrees in mathematics, computer science, violin performance from Michigan State. His work has led to theoretical advances in sensitivity analysis, extensions of classical theory of optimal experiment design, and to new algorithms for supervised classification. The underlying ideas in his work are iterative methods for image reconstruction and reduction of uncertainty through appropriate measurement schemes. His work was recently recognized by Siam Imaging Sciences Best Paper Award. I believe his talk will be a little bit related to that, or maybe more than a little bit. Also, some curious facts about him. He has a Erdős-Baker number 6. If you don't know what Erdős-Baker number is, you can look it up. I know what it is. And okay, so we are very pleased to have you here to give a talk at this workshop. Go ahead.
Great, thanks very much. It's really great to be here. Thanks to Jin Chao and John and all the other organizers. It's a great conference and I'm happy to be here. So yeah, as was mentioned, this is related to the work that led to our Siam Best Paper Award for Imaging Sciences. A lot of this work is with Charlie Bowman at Purdue ECE and some other collaborators. And here's a list of our funding agencies and collaborators. So just a little bit of background about the problem setup. We work a lot in regularized inversion or model-based iterative reconstruction. So the basic question is how we reconstruct some object of interest from some particularly often noisy measurements from some kind of physical system. Here we have a computerized tomography system, a simple 2D reconstruction from these measurements. The Bayesian perspective tells us that we want to predict our measurements from a given X. So we have our object of interest X. We have some kind of physical model of the measuring system that gives us a probability of Y given X. We also typically have a probability of prior measure, which tells us how likely various objects are. We can combine the forward and prior models to give the posterior probability. We take negative log likelihood. So we get a forward model, which is really a data fitting term, and then a prior model, which tells us how likely each one of the possible reconstructions might be. And this gives us what's called the map estimate, the maximum a posteriori estimate. One of the things about this is that the prior model plays a huge role. So this represents 2 reconstructions with a CT system that's embedded in some of GE's scanners. And the only difference here is the difference in the prior model. So you can see that kind of for not such a good prior, maybe an analytically given prior, we get a lot of artifacts. It's very noisy. With a good prior model, we get something which shows a lot more detail and it's much more clinically useful. We'll talk about this later, but this is also related to the bias variance trade-off. You know, our prior model introduces some bias, and the stronger the prior model, the more bias there is. But depending on the class of images that we're trying to reconstruct, the prior model can be very helpful. And this is closely related to some of the things that Ron was talking about. The prior model, in some sense, gives you information about what class of functions or images you believe you might be working with. A big problem in this formulation is that it's really function dependent. So, you know, this forward model, that's fine. We can typically represent the forward model with least squares fitting to some kind of linear model for data collection, or maybe a nonlinear model. The prior model in this form has to be given as a function defined on our space of images, or in 3 dimensions, defined on spaces of volumes. And it's very challenging to develop a functional form for a prior model that gives these kinds of really good results. In fact, so this work started around 2013, 12, 13. Deep networks weren't really so big at that time, but there were still a lot of algorithmic denoisers. There's this denoiser called BM3D, which takes a noisy image in, gives you a clean image back out. And that kind of algorithmic denoiser was much more effective than any kind of functional form for denoiser that we had at that time or have had since. And since then, CNNs have become state of the art for most denoising problems. So the big problem with this Bayesian formulation is that it's not easy to see how we might use an algorithmic denoiser like a CNN or BM3D. And so that's one of the things that this work addresses. So just to highlight that a little bit, we can think about a physical or statistical model. We set up some cost function, and then our goal is to minimize that cost function. And these kinds of models combine naturally in the Bayesian approach. On the other hand, an algorithmic model is much more of a black box. We have some kind of input, we get some kind of output, which is better, but in general, there's no cost function formulation. And in some cases, you can show that the operation of the this black box is not consistent with minimization of some kind of cost function. So the question is how we can apply these kinds of models in a Bayesian approach. So how do we fuse these different kind of heterogeneous models, the minimization kind of model and the input-output kind of model? Okay, so this led to the idea of plug and play, which we'll see is a meta algorithm. So not just a single algorithm, but a way of constructing new algorithms from existing algorithms that confuse these different types of models. We'll see that it's very modular, so you can take things and pull them out, replace them with other things. That's what this diagram is trying to show. We've got a forward model we can plug in or out, a prior model we can plug in or out. And then we'll also describe how this has an alternative formulation as an equilibrium problem. Okay, so we'll start by talking about the roots of plug and play, how it starts with an optimization formulation and then gets reinterpreted in terms of these input-output maps or agents. We'll talk about how this applies more generally, and so what it means to be a meta-algorithm. And then we'll talk about the multi-agent consensus equilibrium, which is a way of understanding what exactly it is that the plug and play algorithm is doing. Okay, so the first part of the talk is about this background and developments leading to plug and play. And this is based mostly on our transactions on computational imaging paper, which received this best paper award this past year. Okay, so just to return a little bit to this regularized inversion model, we have our forward model of log likelihood. And this is often, especially in the case of CT or MRI or various other measurement schemes, pretty closely approximated by a linear measurement model plus noise, which maybe we think of as Gaussian noise, maybe we have some other kinds of noise depending on the circumstances, but we have this to good approximation. Okay, so in this framework, we have our unknown inputs into the forward model, and that gives us simulated measurements back out. We can convert this to a negative log likelihood. So now we get a cost function formulation. In the case when we have Gaussian noise, we can just take least squares estimation. The prior model we think of as given or somehow describing the set of likely images or likely reconstructions. So in the past, like total variations was a typical kind of prior, which is a way of promoting smoothness. But at the cost sometimes of promoting things that look a little bit cartoonish. But in this case, again, we have some kind of cost function formulation that is encapsulated by this prior negative log probability. Okay, so in the regularized inversion, the full model, we combine the forward and prior models and get a full cost function formulation where we minimize the sum of these. And depending on how you want to emphasize the prior versus the forward model, you can put a weighting term here, which can reduce or increase the strength of the prior relative to the forward data fitting model. We can think about this a little bit more geometrically. So in the case when we have linear measurements for our sensor information, then the minimizer is on some lower dimensional affine subspace. This is especially true if we don't have enough measurements to fully constrain the reconstruction, which is typically the case. A lot of times the measurements are expensive. We don't want to necessarily take a full set of measurements to uniquely specify the inverse, or even if we do have a full set of measurements, the problem might be ill-conditioned. So we think of the data fitting term as approximating this affine manifold. The prior manifold is typically not affine, so we represent it here as some kind of curved submanifold in our reconstruction space. And this is based on empirical or some kind of assumed information. And then a regularized inversion minimizes some of these, which we can think of as finding a point which minimizes the distance between these two manifolds. So the genesis of plug and play is to start with this approach, and we'll actually make the problem harder in some sense. So we're going to split the variables. So we used to have f of x plus h of x, and now we've got f of x plus h of v with the constraint that x equals v. So we're minimizing over x and v. It seems like this is just like a totally stupid thing to do. But the point is that it decouples the minimization of f and the minimization of h. And that's important because a lot of times it's much easier to minimize these separately than to minimize them jointly. So that leads to the idea of ADMM, alternating direction method of multipliers. And I should give a shout out to Jim Douglas, formerly of Purdue, who was one of the prime inventors of these alternating minimization methods. So this algorithm takes a step to minimize f and then minimize h, and there's an augmented Lagrangian term to enforce this constraint that x equals v. Okay, and this ADMM algorithm uses the idea of what's called a proximal map. So a proximal map takes some base point as input, and we can think of this, we're going to have some iterative algorithm. At some point, we've got an input possible candidate reconstruction. We want to take one step, not a complete minimization of this data fitting term, but we're going to take one step towards minimizing starting from this base point x. And so we do that we're minimizing this function, but we have a quadratic distance penalty to our base point. So we don't want to move too far from our base point because we have two functions to satisfy rather than just one. And then we have something which controls this step size, which prevents it from going too far. We can get instability issues if our step size is too big, etc. Okay, so then alternating ADMM alternates the application of these proximal map. So we take a step to step towards minimizing f, then a step towards minimizing h. Then we have an update rule. So here we have this Lagrangian term u, which tries to compensate and balance between f and h. Okay, so just to back up just a little bit, this idea of an agent is essentially an algorithmic map that's designed to give you something a little bit better. So an example is exactly this proximal map. It takes some input, a base point. It doesn't completely minimize the resulting image in terms of the function little f, but it takes a step towards minimizing it. And so an example is a denoising agent. You can start with a noisy image, you apply your denoiser, and it gives you this improved output. And depending on how you define this, you could adjust the regularization strength and use that to control the step size. Okay, and so remember, one of the problems with the Bayesian formulation is that we'd like to be able to use these algorithmic models, but the Bayesian formulation relies on these cost functions, but the proximal map gives us a way of converting cost functions to input-output relations. So here we had some cost function. The proximal map takes an input and uses it to produce an output, this minimum, this constraint, or this regularized minimum of little f. Okay, so this gives us a way of fusing these two different model forms that we can use in the plug-and-play algorithm. Okay, so we'll talk a little bit about plug-and-play, describe it as a meta-algorithm, and give some examples. So, so we have this ADMM algorithm. We use this to get a little bit closer to fitting the data. We use this step to denoise the result, and then we update our Lagrangian variable. And the point is that this capital H itself has the form of a map denoiser. So if you look at just this capital H by itself, here's the form of it as a proximal map. And if you recall the form of the Bayesian cost function, we have a data fitting term, which in this case is really, we have a least squares estimate of distance to our input point. And then we have this prior term, which is our original prior term H. So we simplified just a little bit because in the full problem that we're trying to solve, we would have F here to describe how close we are to the actual data. Here, we just have this data fitting term that describes how close we are to our most recent input. Okay, so we've got this input X. We're trying to minimize Z minus X squared. So we just have this kind of white noise, white Gaussian noise denoiser with the prior little h. And so the idea then is, because this has the form of a map denoiser, then why not just apply any denoiser in for this capital H? And that lets us exploit these state-of-the-art denoisers that are algorithmic, BM3D, CNNs, et cetera. It's also very nice from the point of view of a modular software implementation, because as the name implies, plug and play, we can just take this thing out, plug in a different denoiser, and evaluate how the results change. Okay, so that's, it's okay. So I should take just a moment to point out that my collaborator, Charlie, has a great sense of humor. And so, you know, yeah, he helped develop these slides. So we have to put in a few moments of humor. So the big reveal is that for plug and play, we start with this ADMM algorithm, and we don't do anything to the algorithm. We just call it plug and play. But the point is that this idea of changing from a cost function to an algorithmic map was, and still is to some extent, difficult for people to accept because of the sense that we should have some kind of cost function formulation. Okay, so here's a little bit of more Charlie humor. We can plug in our things, and then we just run the algorithm. And you can see here, we're just iterating the various pieces of the algorithm as our algorithm runs. Okay, so you can see that in some sense that this is really a meta algorithm. there are a number of different minimization algorithms that use proximal maps. And we can use this idea to replace any of those proximal maps with some kind of algorithm, okay? So we can plug in different denoisers. We could also learn or have some other kind of algorithmic map that does the forward model inversion, okay? So you could train a CNN or other kind of algorithm to do that without necessarily solving the minimization problem there either. We'll talk more about some of the limitations and pitfalls associated with that, but in principle, you can take these different pieces and replace them with other modular algorithms. Okay, so here's a relatively simple example. This isn't meant to be state of the art or anything. It's just an idea to give you how it works. So the problem here is that our forward model, we start with this ground truth image. We just take some subsamples, say less than 50%, and then we add white Gaussian noise, 5% standard deviation, and we get these noisy subsamples. And then we try to reconstruct the ground truth from these subsamples using this plug and play algorithm. So we maintain fidelity to the data with our forward model, which is just this least squares fit. And then we can evaluate with different prior models. So we have KSVD, we've got this algorithmic map BM3D, which I've mentioned a number of times. We've got a few others. Some of these are cost function based, some are algorithmic, but you can see that the results depend quite heavily on the prior model. And this gives us a way of identifying a nice way of doing this inversion problem, even with an algorithmic denoiser like this. So as you can see, even though this one claims to have the best error, you know, I would say that this BM3D is visually more appealing than this one in terms of comparison to the ground truth. Okay, so when we first submitted the paper, one of the reviewers said, well, is this really plug and pray because you don't know if it's going to converge or not? And that's, you know, a valid question. ADMM has guaranteed convergence for convex functions, at least under the right conditions. So the question then, does plug and play converge when F and H are not proximal map? So the result is that yes, in general, if this F and H are non-expansive, maybe you need a little bit stronger than that, but basically that's what you need, then this result, the algorithm is guaranteed to converge to some equilibrium point, which we'll discuss in a minute. So this at least answers the question about convergence. So here are the original papers. There was a conference paper in 2013, and then our journal paper in 2016. There are a number of variations using algorithms other than standard ADMM. So I mentioned that plug and play is in some sense a meta algorithm. You can take these other different kinds of optimization methods and apply plug and play priors to get a different variant of plug and play. And it's been applied in many applications, super resolution, tomography, Fourier tachography, which we'll talk about a little bit more, et cetera. So it's found pretty wide use in a variety of natural image and scientific applications. Okay, so well, things seem pretty good, but the question is, what problem is plug and play actually solving? You know, we started with some algorithm for function minimization, and then we just replaced some piece of the algorithm with this this black box thing. So what problem are we actually solving now? So how do we explain that? And can we generalize to more than two models, say if we have multiple priors or even multiple forward models? Okay, and so that led us to this idea of multi-agent consensus equilibrium in the SIAM imaging sciences. So just to recap plug and play, we started with cost functions. We have this ADMM algorithm, which leads to proximal maps, which give us these agents. And then that gives us a way of interfacing between these two types of models, cost function minimization and these algorithmic models. Okay, so the question then is, what happens when we start with this algorithm for function minimization, we replace some of the proximal map with agents, and so we get this new algorithm. But then this ADMM algorithm over here was solving this problem. So, what problem is the thing solving? So what problem are we solving if we don't have cost functions anymore? And how does any problem here relate either back up here or over here? Okay, so can we find some problem here that generalizes optimization and that is solved by plug and play? And so can we get this diagram to commute? Okay, so we can think about that in this kind of grid format. We've got a problem formulation in this column, a problem solution in this column. Along the top, we've got cost functions, which we know how to handle well. And then along the bottom, we've got these agents or black box models. Here, we've got an algorithm that uses those. And so here we need some kind of problem formulation to go with those. And that's where our answer is MACE. Okay, so the central question, in some sense, if we kind of back out and take a bigger view, is how do you reconcile multiple of these algorithmic agents, each operating separately on the same problem? And so, each one of these things is working possibly on the same full reconstruction, possibly on separate pieces or different representations, and they each have their idea about how to make things better. And we want to combine the action of all of these into a single problem formulation and result. And while I was department head, which thankfully I've stepped down from recently, but while I was department head, Charlie often said that MACE was a lot like my department head job, because I'd have to get lots of different people who were trying to make things better, but they each have their own ideas about how to make things better. And it's the department head's job to kind of reconcile all those things and come to some consensus equilibrium. So that's what we want to do here algorithmically. So we can actually break that into two pieces. We want the agents to agree, that's our consensus part, and we want them to be in balance, which is the equilibrium part. So we'll focus, there are different variations, but we'll focus just on the case where all the agents have the same input and output spaces. So they're all working on a full reconstruction, for instance. And so for any given input, an agent tries to produce something that it thinks is better. And so here, these are all kind of uncoordinated. They're all just doing their thing, and they're not in consensus. They're not in equilibrium. They're just doing their own thing. So first of all, we want to make them have the same output. And so that's the idea of consensus. So they might have different inputs, but they all have the same output point. And that's the agreement or consensus part. And then to be in balance, the agent vector should sum to 0. So in this configuration, we can see that, well, all these agents think it's kind of better to move in this general up and right direction. So it seems like, we should be able to find some solution up here that all the agents think is better. And so in order to really get a good solution, we not only want them to agree, we want them to be in balance. So here's the consensus, the agreement part. The equilibrium part is that these vector differences between the input and the output should sum to 0. Okay, we can transform this just a little bit, some vector notation, and rewrite it in terms of this vector notation. So now the input points are this x star plus u1 star through u4 star, uj star in general. So now we've represented it in this form. And then a little bit more compactly, we can write it with summation notation here. And then really we're getting to the point of averaging. So if we average this sum, we still get 0. And now we get both the equilibrium and the consensus in terms of this x star, our output point, and these displacement variables. And then since both this average and the output of all these maps are the same point x star, we get this system of equations that encapsulates the full consensus equilibrium. So this tells us that the sum of these displacement vectors is 0. So that gives us the equilibrium part. This tells us that they all have the same output. So that gives us the consensus part. Okay, we'll make it look a little bit nicer by introducing some stacked vectors. So we introduce a new variable that has the input point plus the displacement vector. That's W. We stack all these things. And here we define this G operator, which averages each of the input variables and then distributes them. So this is like a MapReduce algorithm in parallel computing. So then we can do a little bit more rewriting in terms of these stacked variables. And so then the consensus equilibrium condition just becomes this nice equation, f of W equals G of W. So that's our idea of multi-agent consensus equilibrium. So here we started with this idea of just kind of abstractly getting agents to agree, the consensus, getting them to be in balance. And that led us to this nice formulation in terms of these stacked operators and this averaging operator. Okay, so back to our central question, how do we reconcile these multiple algorithmic maps, each operating separately on the same problem? And so this is a simple way of encapsulating the answer to that problem. Okay, and there's a little bit more Charlie humor. We have this MACE representing our consensus equilibrium condition. Okay, so just to look at these operators a little bit more, you can think about this kind of as an input-output diagram. So here, this is extremely parallelizable because each one of these agents is operating, it should be an F sub n down there. Each one of these agents is operating in parallel. And we've implemented this on actually a large supercomputer for a large scale reconstruction problem. And it's very easy to parallelize. This G operator takes all the inputs, averages them, and then redistributes the output, which is also very compatible with large scale parallel computing. Okay, so this MACE framework gives us a way of completing the square. So we have our problem formulation that we claim goes along with the plug and play algorithm on this problem solution frame. Well, we still have to address these problems or these questions because we just came up with this thing a little bit abstractly by defining what we meant by consensus and equilibrium. So the question is, does this generalize this optimization framework in some way? And does the solution of plug and play give us an answer to this MACE set of equations? Okay, so focusing on this problem formulation here. So we start with a map estimate using cost functions. So we're trying to minimize these functions. And then we can think about replacing each one of the proximal maps with agents. So in our cost function formulation, each cost function has an associated proximal map. We can replace those with agents. And when you do that, you can show that that's equivalent to this MACE formulation. So when all the agents are proximal maps, then the MACE solution minimizes the corresponding sum. So it does generalize in that sense. And on the algorithmic side, is this MACE is a problem formulation that's solved by plug and play. And so the answer here is yes. When you have a fixed point of plug and play, then that is a solution of MACE. Okay, so this gives us a nice commutative diagram for the problem formulation and algorithms with cost functions and agents. Okay, so I mentioned briefly the possibility of some variations. So one that we've developed for the application of Fourier tychography, which is a phase retrieval problem, allows each agent to work on a separate piece of the problem. So in Fourier tychography, we have some sample, which is often like an integrated circuit or something like that, and we're trying to probe it using coherent light from a laser. And so we illuminate our sample, we get a diffraction pattern, but we can only measure the intensity, which is really in some sense the intensity of the Fourier transform. So we need to recover the phase and invert. So our measurements in this case are these Fourier intensities, and then we move the lens, move the laser and lens, or equivalently move the sample to illuminate lots of different overlapping patches. And so each agent works on a patch because there's a nice well-defined data fitting term on each patch. And then we need a consistency term that matches up the solutions on overlapping patches. And MACE gives us exactly, very easily, a way of doing that. And in this case, we have to change the averaging operator to incorporate the fact that the agents are working only locally on these individual patches, and there's a varying beam intensity depending on where you are in the patch. But it still fits very nicely into the framework, and we've had very good results and are very competitive with other algorithms. Another thing that we've looked at is changing what it means to be in balance. So, our balance was associated with just a regular average of the displacement vectors. You can also think about a weighted average that lets you easily change the regularization strength, or change the importance of one set of measurements relative to another set of measurements. We also looked at what's known in the signal processing literature as iterative filtered back projection. And you can think about this. So the proximal map, in some sense, it's kind of an implicit gradient descent step. So if you think about R as just a scalar constant, then here, this is a gradient descent step, except we are taking the endpoint as evaluation point for our gradient. So here we have an implicit gradient descent step, and that's equivalent to a proximal map when f is a smooth function. Iterative filtered back projection essentially tries to replace this with a non-symmetric, often a non-symmetric matrix R. It's the filter designed to improve the final reconstruction, but we still get this this kind of implicit update step. But in this case, there's no longer a cost function formulation since it's not symmetric. But we can still use this modified f sub r as one of our agents to define the equilibrium condition. And in this case, when the corresponding agents have cost functions, then we get this slightly modified first order optimality condition where this gradient of f is multiplied by our filtering function r. And what we've shown is that you can get equivalent formulations either by applying this, this implicit proximal map update step with the filtering, or you can use the regular update step, regular proximal map, with this alternate form of averaging that incorporates the filter into the averaging. Okay, and that can be used to improve the efficiency. Because in a lot of cases, this original F is just a linear map, and we don't even need to do any implicit steps as long as we don't have a non-trivial R. There are also other variations. We can change what it means for them to agree. You know, we talked about common output, but we could have common input. And these, in some cases, correspond to different initial algorithms in place of ADMM. And then depending on how you set up the variation, the connection to optimization may be changed. Okay, so, you know, the plug and play algorithm gives one way of solving these equations, but a nice feature of writing it in this way is that then you can start from this equation, the set of equations, and then solve them with other algorithms. So this gives you a way of kind of getting away from an algorithmic centered point of view, move towards a problem centered point of view, and then develop different algorithms to solve it. And so we get a nice parallel modular framework for inverse problems. There are lots of methods or lots of directions we can go next that we're thinking about. So there's still a lot of question about solution methods and convergence, what conditions on the agents guarantee convergence for various algorithms, what algorithms are most efficient for given context, et cetera. There's also a lot of connections that can be made to probabilistic formulations. So, you know, we left the Bayesian framework, and so we no longer have cost functions, we no longer have a posterior distribution, et cetera. But, you know, we still might want to think about how we can sample. In some sense, you could think of this as a generative or sampling a framework that goes along with our formulation of the problem. And this is especially important because, you know, there are a lot of, there's some recent results by Ben Adcock and others about the inherent instability of deterministic inverse reconstruction methods when your measurements are sufficiently sparse. So it's this thing called kernel awareness. And it's especially important to identify, you know, what are the solutions that are consistent with your reconstruction method. As he gives examples in some cases that, you know, MRI reconstructions can potentially miss important clinically relevant features. And so we have other generalizations in terms of consensus or equilibrium conditions, operator splitting methods, and there's a long and growing list of applications. So just to recap, you know, plug and play is this meta algorithm, which lets us start with a lot of different algorithms, plug in new operators. MACE is a way of giving a problem formulation that's consistent with that, and gives us a way of looking for new algorithms which are equivalent but potentially more efficient than our original algorithms. And together they complete this square of understanding about how plug and play relates back to cost function formulations. Okay, so that's it for me.
Okay, so are there any questions, John? In the box.
I do not see any, no.
Okay, Jichao, go ahead. I also have a few, so you go ahead.
You might ask the same question, but anyway, they are Greg, thank you for this great talk. That reminds me of things that Julian and I worked before, of this notion of subspace corrections, alternative projection method, overlapping. You have multi-agent for us called like probably we call multiple subspaces, and you have the things you have overlapping things, right? You have to this is like relate to like our overlapping domain decomposition, overlapping subspace.
Yeah.
And you also mentioned about near the end called kernel awareness algorithm.
Yeah.
When we do the iterations, you know, this is one of the major things which important when you do this alternating iterative method. You have to be aware of the kernel.
Yeah, yeah.
We have all those notions in the context for solving different partial differential equations. So that's totally. And Ludwig and I wrote a paper for Journal of the Journal of AMS, which we kind of in that case we did some linear case. But if you do ADMM type of method, of course, it's in the nonlinear regime, nonlinear method, and I only wrote one paper on that. But anyway, this are the seems like the comments you made, I couldn't agree more. They have all the different kind of algorithms somehow, maybe some relationship.
Yeah. Yeah, no, I think this idea of identifying the limitations is super important. You know, because especially with deep neural networks, like people can train a neural network to do an inversion problem, maybe directly, but don't really address the limitations. Like for natural images, maybe it doesn't matter so much, but for scientific or medical applications, it really matters if your neural network is missing things. And that's related exactly to how well your measurement matrix capturing things.
That's great. Greg, this algorithm you have written in several papers or one paper, we can read something.
Yeah, there are a couple different papers. I have them in the slides. There's one transaction and computational imaging. There's another SIAM Journal of Imaging Sciences.
Okay, we're going to get your slides, right? So okay.
Yeah.
Very good.
There's one question that just showed up actually. Do you have an example that could be turned into a teaching module?
We're working on that right now. So there's going to be an article in SIAM News coming out relatively soon, and then another article in SIAM, the IEEE Signal Processing Magazine. And we're working on developing a code package in Python that could be used to do kind of experimental, kind of a learning module and experimentation module. So we're working on that within the next 6 months or so.
Okay, I have a question, which is more maybe related to the building blocks of this PNP, how to say, framework. So I saw you said that ADMM and also PNP are convergent methods. So let me take some simple example of quadratic minimization with constraints, right? That will be convergent, all right? But does anybody knows anything about the rate? Because if the rate is like infinitely number of hours, then in some sense, I mean, this is a little bit. So can you say something about, is there any cases in which rate of convergence has been established? That's my question.
Yeah, no, there's a lot of work on ADMM and related algorithms in the convex optimization setting. So if you make strong enough assumptions, so it's a little bit like what Ron was saying, like if you make strong enough assumptions, then you don't have to work quite as hard, right? So if your functions are strongly convex, then you can use the parameter for strongly convex to give a rate of convergence. And there are lots of other criteria you can use. For the case of more general maps, so I mentioned that in the case when it's non-expansive, when the agents are non-expansive, then you get convergence. But again, you can, so non-expansive basically means Lipschitz constant equal 1 or less than or equal to 1. So if you make your Lipschitz constant strictly less than 1, then you can use that Lipschitz constant to guarantee convergence rates. I mean, so in practice, algorithmic denoisers are probably not non-expansive in general. Because like if you train a neural network to do denoising, in general, it's not going to be non-expansive. You can give examples when you know, you take two kind of dissimilar images, you denoise them, and they get farther apart. But locally, you expect that generally it's going to be non-expansive because, you know, you'll take a noisy image and move towards a cleaner image. And so you expect that at least in some local neighborhood of your solution, you expect that the conditions are more or less satisfied. So yeah, but you know, my career started very pure, and then it's gotten less and less pure over the years. So more applied, but also like more applications oriented. And so in the end, people really care about, does it converge in practice, which in most cases it does for our applications, and does it give good results that are reliable? And that's associated with this idea of kernel awareness and the right prior.
The kernel awareness, Greg, is there? I'm curious because we also have this kind of technology.
Yeah. So in this context, they're talking about the kernel of the measurement matrix. So so you have this measurement matrix A. So you take your object X, you multiply by A, and you get measurements like the sinogram or something.
So this sounds very familiar to me.
Yeah, but so then, you know, like a lot of times people don't want to take a full set of measurements, either because it's too much X-rays or whatever, or it takes too much time. And so they do sparse view reconstruction, which means that you only take a relatively limited number of different views or measurements. And because then there's not enough information to fully invert, then your measurement matrix has a non-trivial kernel. And so this kernel awareness means that if you have an algorithm that takes two different sets of measurements.
You put them together, you should get all the kernel.
Well, the problem is when you have two different sets of measurements that differ mostly by something that's in the kernel. Okay, and if you can reconstruct both of those well, then you must have a large Lipschitz constant. You must be kind of expanding something very, very highly, and that's when you can miss something. So basically it means that like you can take something which looks normal, a normal reconstruction, but change the measurements very, very slightly, and there'll be like an important clinically relevant feature that you missed.
That's really fascinating because you know, the subspace correction method, we want to, the kernel of the big things you want to solve can be distributed around in the subspaces. I don't know if that's related.
Yeah.
I just want to make a comment about what Ludmila, I just, when I was in Stanford a couple of years ago to give a short course, I was talking to people there. This ADMM has hundreds of papers.
Oh yeah, yeah.
Which are very much related to what you and I do. And if you think about you mentioned about this result about each variable, the mapping is a contraction. This is kind of similar to like our omega should be less than 2, you know.
Right.
You know,
Yeah.
So the iteration should converge.
Non-expansive, right?
Right. Yeah.
The iteration is going to be at least it's not going to. You have strictly contraction, then converge, you know that. But the thing is that somehow there's lots of overlapping of these two fields. I actually wrote a paper with Professor Yin Yu in Stanford. Somehow I put it on archive, then we didn't have time to get it published. But there's tons of papers in the subject. And but anyway, so it is amazing that you have all this applications. I thought that was just a mathematical game. but apparently this is something very, very relevant.
Yeah, for sure. Yeah, ADMM is.
So this kernel awareness is also in one of your papers, right? I just want to.
We haven't. That's something we're working on right now to develop further, but it's in a paper by Ben Adcock at Simon Fraser. He used to be at Purdue. Now he's at Simon Fraser.
Yeah, that's great. Yeah, that's great.
Yeah. Any other questions, Jonathan, in the box?
I don't see it. That's
Okay.
All right. Well, thanks very much.
Yeah, well, thank you for the very interesting talk.
Thank you, Greg. Thank you. This is great.
Good. All right. Well, thanks very much. Yeah, it's great to be here.
I want to talk to you more later, but anyway.
Yeah, sounds good.
So, Rachel, if you would try to share your screen.